So next I want to tell you a bit more about this idea that we had of transparently lifting existing analysis and why this works with SPL lift. So again, let us assume that some static analysis programmer has implemented some static analysis problem, right? So this problem here could be any IFDS problem instance. For instance, this could be like I told you, a reachable definitions analysis, or possibly uninitialized variables analysis or attained analysis, maybe even some limited type state analysis, something like that, right? And normally, for instance, using our Harris framework that we actually use to implement this prototype, you would simply pass this problem to an IFDS solver, and you would call solve, and it would solve it for you. Now, what's really nice about this is that you can now using SPL lift, the very same unmodified problem definition. So you don't need to change a single line of code of this IFDS problem here. You then simply use another solver. Now this time we use this SPL IFDS solver. And optionally, we still provide a feature model. So that gives us a Boolean constraint, basically, that the analysis should consider, like I just showed you. And then we call solve, and it does all the magic for you. So as an analysis programmer, you don't even need to have heard about product lines, right? You can simply stick this into the right solver, and it all works magically. And then these are the results that you get. So where normally in the IFDS solver, for any statement, you would be given such a result, right? So basically a set of data flow facts that hold at this given statement. Now here, you're basically given a constraint mapping. So you're given a map that maps from facts that can hold at this given statement to a constraint. Here it's parameterized through a string because the constraints are labeled with individual strings. But that's not important. So it's basically a mapping from a fact to a constraint under which this particular fact holds, right? So this could tell you the variable x, for instance, is tainted if f and g hold, right? So this is a Boolean constraint. And now the setup basically looks like this. So previously in this Harris framework, we had implemented the IFDS solver as a particular extension of the IDE solver that was using such a two-element lattice, right? So using top or bottom or true and false. And then we used the SUT framework to implement these particular IFDS problems for this solver, right? And we had particular concrete analysis that extended this abstract superclass here, actually. Now, in SPL lift, we then have the specialized solver that uses constraint lattices, right, or a constraint lattice. So that basically replaces this two-element lattice by a constraint lattice. And here we actually use Java BDD, which is a BDD library for Java, to implement this. And the product lines and the feature model we support in particular in our prototype SPL lift, they were actually derived using a so-called, a certain feature IDE called Site, which allows you to actually define these software product lines, in this case for Java. So the prototypical implementation that we had that looked like follows. So it basically used this feature IDE, this colored IDE Site that you see here. So this looks a bit old school, but actually this tool now is already also like 10 years old. But basically, like I said, it allows you to define product lines for Java, right? So using a regular Java program, you were able to actually color individual statements here, or also parameters, for instance, to tell the compiler, or in this case, the program analyzer, that the statement, for instance, here, it's only present in the code, the statement or this declaration here, if this particular red feature is enabled, right? So that's similar to an if-def, except that the if-def is not literally in the code in terms of text. Here it's done a little bit differently by coloring these different statements. Now, currently ongoing, we actually have an integration with Phaser. So Phaser is our analysis framework for C and C++. So it's based on the LLVM compiler infrastructure, and that looks a little bit different. So here it actually uses the Clang front end to parse C and C++ source code into LLVM IR. So that's a sort of LLVM's Gimple representation. It's a little different from Gimple, but the differences don't really matter here. Yeah, we have extended Clang actually to be able to handle preprocessor annotations. And the result is then basically a variability tagged LLVM IR. I will still be showing you a couple of examples of this later. That's what we are doing now. But yeah, back then we were rather using this feature IDE that you see here. Now, let me tell you what results we obtained using this feature IDE-based approach. So again, these are the same benchmarks and the same example analyses that I showed you earlier. So in blue here, again, you have the times that it took or would have taken to analyze these different product lines using the product-based approach. Now, these are the analysis times that we got with SPL-Lift. And as you can see, this is really a dramatic improvement, right? So in some cases, maybe not so much, right? So here we brought it down from 189 seconds to 85. That may not matter that much to you, but Lampiro also has very few configurations, very few features. But in particular, for the benchmarks where it really mattered, right? Like Berkeley DB and GPL, where the analysis typically would have taken days or even years, this now goes down to several seconds or minutes in the worst case, right? So here, it still scales dramatically better than it did before. We're still, or at least back then, we were still not very happy with the results. It still took several minutes. So this is in the order of 12 minutes here, right? That had to do with the fact that the constraints were still growing relatively large. And like I told you, they are expensive to handle. So this is still subject to ongoing research to make this better. But still, the improvement was already pretty good. Now, there's an interesting story behind this, right? So when I first implemented this together with my colleagues, I thought this might be a good idea, right? I thought this family-based approach might work. And then I implemented this in this prototype and we did the experiments. But when I saw the numbers, I was actually blown away. So I would have thought that there were improvements, but not such dramatic improvements, right? So, I mean, going down from years to minutes, I would never have dreamed of this, right? So it's really a dream come true. So only then I was actually going back to the drawing board and I was wondering myself, why actually is it so fast, right? I mean, because I was really, for a while, I was actually doubting that it was correct, right? It could have been just an implementation fault. But then in the end, we actually double checked that the results that we are computing, they're actually identical to the ones that you would compute in the product-based approach. So there was no implementation mistake. It was really that fast. And that's an interesting story, actually. So recall the complexity, the theoretical complexity of IDE. The complexity of IDE, I told you, is bounded by this constraint here, right? So it's linear in the number of exploded supergraph edges. So it's linear in the size of the program, you could say. And it's cubic, in the worst case, in the size of your domain. But importantly, in IDE, this is not your entire domain. In IDE, D is only the part of the domain that relates to your nodes, right? To your supergraph nodes. And this constraint is independent of the size of L, which is the lattice that you are using to compute the jump functions, right? Or edge functions. So this does not at all show up here. What does this mean for IDE? Well, sorry, for SPLift. Well, in SPLift, L is actually the lattice of Boolean formulas. So the size of L is actually the number of Boolean formulas, right? And this is actually what can grow large, right? So I told you we can have a large number of different Boolean formulas. It's exponential in the number of features you can have. But this is not at all part of the equation. So it basically means no matter how large these formulas grow, the IDE solver will always take the same time. Now you might become a little bit dubious of that statement, right? So is that really true? Well, it's not quite true because this constraint here, it actually assumes that well, the composition and join operations on the edge functions, and that means here on the Boolean formulas, they actually take a constant time. And that is not necessarily true, right? So I told you that if you do a conjunction and disjunction of a BDD, for instance, it's not typically a constant time operation. So it's a polynomial time operation. So that means this estimate here for SPLift, it's not entirely true. So it's not generally true for formula operations and or. And it's also not true about BDD operations. So for BDDs in particular, the growth of BDDs, it seems to be bounded linearly in the size of the program. So that's something I didn't really prove, but that's something that seems intuitive from the way we construct the analysis, and the analysis constructs the exploded supergraph. So that's already somewhat encouraging, right? So there's a linear growth in the size of the BDD. But the question is then, how many individual fact propagations does SPLift actually save compared to a product-based approach? And that's something I want to show you on the next few slides. So let's assume we have a starting point as main, and we are starting our analysis from there, and we have some data flow here, okay? And at the beginning, assume that we have a configuration space of 16 configurations with no feature model. So that means we would have 16 different software products, all of which have the same data flow here that needs to be tracked, okay? Now, if now SPLift computes such an edge here, such as jump function true, then this means that in the product-based approach, we would have 16 different individual analysis runs, each of which compute the same data flow edge, okay? So here we have one operation that is already representing 16 operations in the product-based approach. So it's the entire configuration space. Now, if we have such a feature constraint F, this gain that we have here, it is further reduced, because now with F, F basically only represents 8 configurations, right? Because basically means we now have a reduced configuration space of all the 8 out of the 16 configurations in which F actually holds, right? So now the savings, they are still there, but they are smaller, right? So here we basically saved 15 out of 16 computations. Here we saved an additional 7 out of 8 computations. And this goes on and on, right? So if we have a not G here, basically this configuration space is further reduced. So here we would save 3 out of 4 configurations and so on, right? So you can simply count this. In the end, you would have 16 plus 8 plus 4 different computations in the product-based analysis for these different products that are induced by this product line here. But here we only did 3 computations, so 25 we actually saved. So that means in the end, product-based analysis does have exponential cost, but SPLift, it brings this cost down by analyzing the entire software product line in one single pass. And the feature constraints in the IADE solver that we're using here, they model variability. We used BDDs to support an efficient encoding of constraints. And this can nicely be combined with any IFDS-based analysis, right? That's really the beauty of it. You can use any IFDS-based analysis. And we actually have a planned integration, or it's actually an ongoing integration with Phaser that should allow variability analysis of any C program. And that I still want to talk about a little bit on these final slides. So we have currently re-implemented a variant of SPLift for actual if-defs and actual C code. So one of our goals is, for instance, to analyze the OpenSSL code base that I talked about earlier. And currently this already allows us to analyze such real-world code bases. So we currently have that capability. We have an implementation based on Phaser and also on Super C. So Super C is basically a variability-aware parser that was developed by some colleagues of ours from the United States who are collaborating with us on this project currently. And we're using Super C to first convert the C program that has if-defs in it into a C program that only has regular C-based conditionals. That's really what Super C here does for us. So it's sort of doing a so-called desugaring of this if-def enriched code into regular C code. Let me show you what this looks like in this example product line that we have here. So here we have, for instance, a function header definition in C. So that's defining a function header for a function whose implementation is defined somewhere else. And that is guarded by a feature M1. Okay. Here we have a matching function definition that is guarded by a feature M2. And here we have another function definition G that is calling this function F, and that is unconditional. Okay. Now, what does this lifting or this desugaring actually give you? Well, it's basically, first of all, renaming this function here, okay? We have to do this because we are now putting both of these definitions here into the same code base, right? So you basically cannot have both of these at the same time, right? There would be conflicting definitions, and that's why we are renaming them here, right? So we are saying you can have a definition F1, or you can also have a definition F2. And we're doing some internal name mangling to keep track of the fact that originally both of these were named F, and they were located at these lines of the code, right? So there's some mapping that we keep track of internally to have some traceability. And then here, where we have this call to F, we are basically generating this code here. So it's telling us if you have M1 enabled and not M2 enabled, then this call should go to F1, because in this case, this is the relevant function definition that is called here. In the other case, where M2 is enabled and M1 is disabled, then the call should go to F2, so to this function definition. And in all the other cases, we should actually have a type error, okay? So that means basically the code is not, it's not valid, right? It doesn't type. This might look a little bit odd, right? Because what does this mean, right? I mean, you sort of get a C program that is equivalent to all the possible programs from this product line. And it's even a runnable C program, right? So I could run this. And depending on how I instantiate these Boolean flags here at runtime, I get the right behavior, right? So F1 is called or F2 is called. And if I enable both M1 and M2, then I even get this dynamic type error, right? So that's not a type error that's thrown by the compiler. That's a type error that I will then obtain at runtime. So that's already kind of useful, right? So, but the point is, we don't really want to run this code, right? So our intention with generating this code is that we want to make it analyzable by basically an almost off-the-shelf static analyzer for C programs, right? So you could actually now give this to any static analyzer for C, and it could already pick up these different procedure calls here, right, or function calls, and it could already tell you that maybe you have some interesting or violating data flow in this program. But an off-the-shelf static analyzer would now not be able to tell you under which constraints these data flows can happen, right? So because a regular off-the-shelf static analyzer, it would ignore these constraints here, right? It would basically assume anything here. So it could tell you, yes, there can be a data flow anywhere in your product line, but it doesn't tell you for which configurations. And that's why we went beyond this. So in the second step, we actually implemented a special analysis that recognizes these conditionals. So basically in our sort of SPList variant for C code, we recognize that this is a special Boolean flag that was inserted by us. So it's a static Boolean flag. We can even do some constant propagation here in case these are constantly set. And then we recognize this. And for these constraints, we are then actually computing a feature constraint like we did in SPLift as well, right? So we are symbolically evaluating these constraints. We're keeping track of them, and we are propagating them through the program using an IDE solver like I just explained to you, right? And so what this lifting gives us is it gives us an easier syntax, right? So now our static analysis, it can deal with regular C code like you see here. It does not actually have to take care of these if-defs. It does have to understand these conditionals though. We did an additional extension over the SPLift approach that I explained to you so far. So in the original SPLift approach, we were only able to lift IFDS-based analysis, right? So I told you we are assuming that originally you were using this Boolean lattice, and we replaced that with a feature constraint lattice. But now here we took an even different approach. So here you can actually also use IDE in the first place for your original analysis. So you can actually lift, for instance, linear constant propagation. And the way this works is that we basically now take the lattice that you are already using in your IDE-based analysis, and we are converting this into an extended lattice using basically a Cartesian product construction. So we are augmenting your lattice with our lattice so that we are computing whatever the original IDE-based analysis was computing and our feature constraints at the same time alongside that. And this basically gives you more expressiveness and yeah, allows you to now lift concept propagation as well. That's all I wanted to say about SPA lift and its current application. So we're currently in the phase of actually assessing this. So we have run some initial experiments. They're already encouraging, but they already showed us that there are some yeah, interesting challenges still. So for instance, something that we did not foresee is the following, right? So if you look at OpenSSL, for instance, we might analyze it, or we might try to analyze it, but then during this lifting approach, or during this desugaring that I'm showing you here, we might produce code that is not actually even valid on the current platform. So for instance, you might have an ifdef that tells you include the following code only if you're running on Linux and not maybe on a BSD variant of Unix or anything like this, right? But then if we desugar this ifdef goes away, right? And we include this particular statement no matter what, right? I mean, it's still guarded or by these conditionals, but these are runtime conditionals, right? And now the problem is that if we want to analyze this code and it was actually written for a different platform, that might make the code itself unanalyzable on this platform on which we are conducting the analysis, right? So let's say we are running this static analysis on a BSD platform, but the code we are analyzing was actually generated for a non-BSD platform. Then on the platform on which we are conducting the analysis, we might not even have the right header files, right? So it's really a technical issue, but it really is a real world technical challenge that you need to deal with. It's, there's no conceptually nice solution to it. We're currently investigating how feature models can help, right? So feature models can maybe constrain the configurations that we're investigating and so on. But yeah, this all needs to be dealt with if you want to make this happen on real world code. But that's the current status of it. So that concludes what I wanted to say about product lines. Just an outlook into what comes next. So we have now talked about sparse IFDS, so interesting variant of IFDS. I've talked about SPA lift, which is basically an extension of IDE, as you can see it at least this way. Now in the next couple of weeks, I want to talk about other extensions of these two frameworks, namely pushdown systems, which are basically a relatively elegant and lightweight way of computing static analysis that are very similar to what you can do with IFDS. And then in the week after that, we will also be talking about weighted pushdown systems, which are a similar extension to IDE, I would say. So weighted pushdown systems are an extension of pushdown systems, but these two relate to one another in a very similar way in which these two relate to one another. But I'll explain more about this in the upcoming week. Until then, yeah, enjoy the rest of the week and have a good one. Bye-bye.